Every single time you take a step, drop your keys, or even just sit completely still in your chair, there is a hidden tug-of-war happening all around you. Welcome to this explainer. Today, we are demystifying the invisible pushes and pulls that dictate absolutely everything in our physical universe. We're talking, of course, about force and motion. So let's dive right in and make the invisible, well, visible.
Quickly, here's our roadmap for today. We're going to cover mass versus weight, types of forces, measuring forces, the effects of force, action and reaction pairs, and we'll wrap it all up with the magic of buoyancy.
All right, kicking things off with Section 1, mass versus weight.
Now, I want you to really think about this for a second. Are mass and weight the exact same thing? In everyday conversation, we use these words totally interchangeably. We're always talking about how much something weighs when technically we really mean its mass. But in the realm of physics, they absolutely do not mean the same thing, not even close.
Here's the breakdown. Mass is simply a measure of the amount of matter in a body. It only has magnitude. It's what we call a scalar quantity, measured in kilograms. And crucially, your mass is constant everywhere in the universe. Weight, on the other hand, is a derived vector quantity. It actually measures the gravitational force acting on that mass. It always points toward the center of gravity, and we measure it in newtons. Because weight depends entirely on gravity, it varies. Think about it. If you weigh 600 newtons here on Earth, you'd only weigh about 100 newtons up on the moon. And in deep space, your weight would literally be zero, while your mass stays exactly the same.
Moving right along to Section 2, discovering types of forces. Let's categorize these pushes and pulls.
Two of the most common forces we encounter actually act very differently from one another. First, you have gravitational force. This is that constant pull pointing directly towards the center of the Earth, causing everything thrown upwards to eventually fall back down. Like the classic apple falling from the tree. Contrasting with that, we have elastic force. Now, this force doesn't just hang around all the time. It only appears when a material is stretched or compressed. Think about drawing back the rubber band on a slingshot or pushing down hard on a metal spring.
But here's a really crucial point. Forces don't just pull things down or snap things back into place. They also resist. Imagine trying to push a heavy wooden box across the floor. Frictional force is that stubborn, invisible resistor that exists between two surfaces in contact, and it always, literally always, acts in the exact opposite direction of the motion. If you push that box forward, friction is right there pushing back.
Finishing up our categories, we have two very specific reactive forces. Normal force is produced whenever an object makes contact with a surface. Honestly, it's the only thing keeping you from falling straight through the floor right now. Then there's buoyant force, which is the upward thrust acting on an object that's floating on the surface of a fluid.
Okay, Section 3, measuring invisible forces. How do we actually quantify all this?
To put all this theory into practical application, we can measure force using a really simple tool called a spring balance. If you hang a 50-gram weight at the end of it, the spring stretches, giving you a direct reading of the gravitational pull, the weight. But you can also lay that exact same spring balance flat on a table to measure frictional force. If you pull a wooden block across a smooth surface until it just starts to move, you'll get one reading. Try repeating that exact same pull on rough sandpaper. The reading on the spring balance is going to be significantly higher. It's showing you exactly how much extra force you need to overcome the increased friction.
When we record these measurements, we use the standard SI unit of force, the Newton, represented by a capital N. And remember how we said force is a vector quantity? That means it has a magnitude, like the number 10 right here, and a specific direction. So if someone applies a pushing force of 10 newtons to a box, we know exactly how strong that push is, and the point of application tells us exactly where it's headed.
Let's jump into Section 4, the effects of force. What actually happens when things get moving?
We generally just think of force as the thing that makes stuff go, but a force can actually have 5 distinct effects. Yes, for sure, it can move a stationary object, but it can also stop an object that is already in motion. A force applied from the same direction can change an object's speed, ramping it up to go faster. Apply that force from the side, you'll change the object's direction. And, maybe most interestingly, if you apply force to something malleable, like a lump of clay or an aluminum can, it can completely change the shape and size of the object itself.
Moving on to Section 5, action and reaction pairs. Because forces, well, they never act alone.
Consider a perfectly stationary book just sitting on a table. At a glance, it looks like absolutely nothing is happening. But there is actually a fierce, perfectly balanced battle going on right there.
The book has weight. That's a gravitational force pulling it down. We call that the action force. So why doesn't it just fall right through the table? Because at the exact same instant, the surface of the table is pushing back up with a normal force. That's our reaction force. The book stays completely still because the magnitude of that downward action force is exactly the same as the upward reaction force.
We can see this play out in motion too. Imagine two little trolleys pushed together with a compressed spring trapped between them. The second you let go, that spring exerts an elastic action force on the first trolley. But at the exact same time, the second trolley experiences an elastic reaction force. The incredibly cool part about this, both of those forces have the exact same magnitude, but they happen in totally opposite directions. The trolleys launch away from each other, traveling the exact same distance but moving completely apart. Action and an equal but opposite reaction.
And that brings us to our final stop, Section 6, the magic of buoyancy. Let's talk about floating and sinking.
Whether something floats or sinks entirely comes down to a battle between its downward weight and the upward reaction force of the fluid, which we call the buoyant force. And the ultimate deciding factor here, density. If an object, let's say a piece of cork, is less dense than water, its buoyant upthrust force is actually greater than its weight, so it floats. Conversely, if an object is denser than the liquid, think of a chunk of iron, lead, or gold, the buoyant force is less than the weight of the object, which causes it to sink straight to the bottom.
And this right here brilliantly illustrates why understanding physics is so incredibly empowering. Think about a massive cargo ship out on the ocean. It's made of thousands of tons of heavy steel, a material that is vastly more dense than water. By all common logic, steel should sink. But engineers use their understanding of these invisible hands by shaping the ship's hull to displace a massive volume of water. They ensure that the upward buoyant force acting on the ship is perfectly, flawlessly balanced against the immense downward weight of the steel and its cargo. It's an action and reaction pair, beautifully balanced so that thousands of tons of metal can just effortlessly glide across the ocean.
So we've explored the fundamental difference between mass and weight, we've measured friction and gravity, and we've seen how action and reaction pairs can even make thousands of tons of steel float. The physical world is entirely governed by these hidden pushes and pulls. I want to leave you with this provocative thought. Now that you actually know how to see them, where are you going to spot these invisible hands at work in your own life today? Next time you push open a door, drop your keys, or even just sit down in a chair, take a second to appreciate the magnificent, perfectly balanced forces holding your entire world together. Keep exploring, and thanks for joining me on this explainer.